Okay, so in part one, I showed you guys how to find the line of intersection between two planes using a system of equations method, and we found the answer in parametric form. So here I'm going to show you a different way to approach this problem using the cross products of vectors, and it's going to give us an answer in vector form. So check out part one if you want to see that. So given our two plane equations, we can write the normal vector that comes perpendicular to all points on the plane as just these three coefficients here. So the coordinates in x, y, and z for p are 3, 2, 1. And for q, it's 2, -1, -1. So again, we're just taking these coefficients here, plugging them in there. So to find the line of intersection, we need a line that is going to be perpendicular to this norm and perpendicular to the other norm, the norm for Q. An easy way to find a vector that's perpendicular to two different vectors is to take their cross product. So, and this is going to be the directional vector for our line. So we're going to call it V. It's going to be equal to NP cross NQ. And it's going to be equal to the following determinant. Hoping you guys, I'm assuming you've seen this before, but I'm going to go over everything just to refresh your memory. So we have a 3x3 matrix, which we're going to find the determinant of. We have our I, j, and k unit vectors up top. So a good trick for solving these 3x3 determinants is to start as if you're writing out the matrix again, just repeating the first two columns, and then leaving, you don't need the third one. And then look at these diagonals here. So do highlighter actually. So I to -1. Okay, so we're going to look at these diagonals and we're going to multiply them out. So here I to -1, we get -2i. J times 1 times 2 plus 2j. K times 3 times -1 minus 3k. All right. And now we're going to look at some of the reverse diagonals. So they're going to go the other direction. And since the way I remember this is we're actually going to be subtracting these next three numbers, but since they're kind of the reverse, you can think of it as, since they're going reverse, they get a minus sign. So k times 2 is 4k. I times 1 times -1 minus I. J times 3 times -1 minus 3j. So distributing this minus sign in, we're going to get minus 2i plus I, so minus I, plus 2j plus 3j plus 5j, minus 3k minus 4k is minus 7k. Which we can write this in component form like that. And that is our directional vector for our line. So we're actually almost done. The only thing is this, if we just leave it as is, isn't the line of intersection. It's just parallel to it. So it could be any of these lines in 3D space. We actually need to give it a point to start at to anchor the direction on the line we want. So that's going to be in the form v times a parameter t plus a v naught, which is just some point on the line. And an easy way to find a point is if you set z equal to 0, we're going to have two equations for x and y, and we can just solve that to get a point that's going to be on this line. So setting z equal to 0, p is going to be 3x plus 2y equals 3. And q is going to be 2x minus y equals 4. So this is us solving for v naught. And this is a pretty quick system of equations. This means 2y equals 3 minus 3x, or y equals 3 over 2 minus 3 over 2x. And we can plug that into the other equation to get 2x minus 3 halves plus 3 halves x equals 4. So 4 halves plus 3 halves is 7 halves x. And then we're moving 3 halves over to the other side. So 8 halves plus 3 halves is 11 halves. Multiplying by 2 over 7. X equals 11 over 7. Almost there, so plugging this back into our equation for y, 3 halves minus 3 halves times 11 over 7. So we're going to have 33 over 14, a little messy here. Multiplying the top and bottom by 7 here to get this over 14. 21 over 14 minus 33 over 14. It's going to be minus 12 over 14. Okay, so our point here, plugging this, bringing this all together, we set z equal to 0, and we have x equals 11 over 7, and y equals negative 6 over 7. So our v naught is 11 over 7 minus 6 over 7, 0. And finally, if I can squeeze this in here, our line of intersection is -1, 5, -7 times t plus 11 over 7, -6 over 7, 0. So I think this is a little faster than the other method, the system of equations method, but you do have to take a cross product and use some vector properties. So there's no bad way to do it, whatever method you prefer. And again, this is going to give us the vector form of the line. So if you need it in parametric form or symmetric form, check out my next video to see how to switch to those forms.